Here we are. So our first talk will be from my colleague at VMware, Yi Hung, and he's going to be talking about rewriting critical bits of Open vSwitch in Rust.
Okay, good morning, everyone. Okay, sure. Okay.
So when you hear on the PA system, recording has stopped or recording has started, don't be alarmed. We are just trying to make clips for each sessions instead of having one 8-hour session or 9-hour recording and then chopping it up. It's just easier for us to manage the recording so that we can post it later. That's all. So we're just trying to locate the slides. It's the teething pains and try to get that together. Aaron's gone.
Okay. Okay, good morning, everyone. Today I would like to talk about how to make OVS to be more memory safe by using Rust. This is joint work between Ovidia and I. So we all know that OVS is written in C, and C provides us a lot of freedom of control of use of memory. But this is kind of like a double-bladed sword, where it also introduces tons of memory safety issues, such as you can access of uninitialized or deallocated memory, dangling pointer, and it can lead to memory leakage, so on and so forth. And all this memory issue can lead to serious security hole or system crashes. Like this is an example that our customer have that after OVS start for 20 minutes, it kind of eats up all the memory for 400 gigabyte only due to a small memory leak in the fast path. And if we look at the Git repo, we can easily find tons of different fixes, either on memory leak or null pointer dereference. So we kind of think of a way to get rid of this. The current approach we have is run some sanitize tool either on the compile time, such as address sanitizer, undefined behavior sanitizer, or run Vagrant in the runtime, hoping that our unit test can coverage those cases, those memory leak cases. Or alternatively, we may use language like Java or Python, where they have runtime to keep track of the memory level allocated. However, this language, they rely on the garbage collection mechanism, which may kick in at unpredictable time. So it may hurt the performance, which is not good for writing system software like OVS. So that's why Rust comes into the picture. So what is Rust? basic Rust as a system programming language where they have many features, but in this talk we mainly focus on the memory safety. So so they provide memory safety without sacrificing performance. You can think of C or C++ as a language that have more memory control, but they are less safety. And other language like Java or Python, they have less control memory, but they provide more memory safety. And Rust can provide you both without sacrificing the performance. In the following, we are going to look at a few Rust examples to see how it can help us to reduce the memory safety issue. The first thing I would like to talk about is through this small example to talk about an idea in Rust called ownership. So this is quite basic. Basically, we dynamically allocated a memory space to slow the string hello world and assign it to S1. We're just trying to print S1. The nice thing about Rust is the compiler will detect once the owner of this particular space or memory goes out of scope, you directly free the memory. So it's not possible for a programmer to forget to free the memory. So there's no memory leak, which is kind of nice. And so this example is just, we just have another statement where we assign S1 into S2. And let's try to print S1. But however, the compiler will report in compile here. It is because in a statement of S2 equal to S1, it will transfer the ownership from S1 into S2. So S1 no longer owns the memory. So there's no point for us to print S1 here. So it's kind of idea code borrowing. And let's look at the other example here. So how can we make both S1 and S2 to get the memory? So we can just put an AND sign in front of S1. So it means that it's an immutable borrow, so that S1 is still the owner of the memory, and S2 now kind of borrowing the memory from S1, so that both S1 and S2 can print over here. The other example is like this. So we just add some curl bracket around the statement S1 and S2. Like in this example, actually, the compiler will also report an error here. It is because once S1 goes out of scope, the memory of S1 will be free. So S2 can no longer access the memory over here. So this is an example that shows us how can we use Rust to avoid like use after free type of memory error. Another example is Rust will kind of remind us if we use some of uninitialized variable so that we don't have this hyper memory error. Okay, so for this project, basically we use Rust to rewrite the miniflow extract function in OVS. We pick up this function because this is a kind of important function for every single packet that's run in the fast path. And we used to have some serious bugs over here. And the implementation is rewriting this in Rust and build this as static library linked with OVS. We run some performance tests and compare it with the AFSGTV.path with C implementation. We see a slightly performance drop, but it's kind of close because we spend more time on checking some memory boundary, and our code is not fully optimized yet. So if you are interested, you can go ahead and check out our GitHub repo. And so in this talk, we basically shows a few examples of how Rust can prevent us from running into some memory issue, and we run some tests. And here's a list of feature work that we would like to work on. Yeah, that's pretty much it. Thank you.
We have time for one question, I believe. Does anybody have one?
Very interesting. Is there any plan to integrate this work or to put it into upstream?
Yeah, currently it's an experimental work, so we are exploring the possibility to put it upstream. Yeah, but.
All right, let's thank our speaker one more time.